So in the last class, we have taken an example of a producer-consumer process where we have assumed that the producer produces items and puts the items into a buffer of size n. The buffer is arranged in the form of a circular buffer, and the consumer process consumes the items from that buffer. And we have also seen that in the first algorithm that we had given, where the buffer full and buffer empty conditions are checked by checking the pointer values in and out. Okay, and there the problem we have pointed out that if we use in and out pointers to check the buffer full or buffer empty condition, in that case at least one of the locations in the buffer pool must be empty. Okay, that means if we have a buffer of size n, at the most we can put n minus 1 number of elements into the buffer. Okay, so to avoid that problem, what we have suggested is, let us use one more variable, say count, where count will give the value of the number of items that are present in the buffer. So whenever a producer process produces an item and puts into the buffer, it will check what is the value of the count. If the count is equal to n, that indicates that the buffer is full, so the producer process cannot put the element into the buffer. Okay. Now whenever the producer process finds that the count is less than n, that means there must be at least one location empty in the buffer where the new item can be placed. Okay. So the producer process places the new item into the buffer, and after placing the new item into the buffer, it increments the value of the count by 1. Okay. Similarly, the consumer process, while trying to consume an element from the buffer, it checks whether the count value equal to 0 or not. Count value equal to 0 indicates that the buffer is empty, so the consumer process cannot consume any item from the buffer because there is no item. If count is greater than 0, in that case only the consumer process can consume an item from the buffer. Okay. So obviously after consuming an item, it has to reduce the value of count by 1, because now the number of items, number of elements present in the buffer is less by 1. Okay. So by making use of this count variable, we can use all the n locations in the buffer. That means if I have a buffer of size n, I can put n number of elements into the buffer maximum. Okay. Then I just pointed out that if we use this simple algorithm, this is also not problem free. This algorithm also leads to some problem. So let us see what is the problem that we will face. Now whenever the producer process places an item into the buffer and increments the buffer by 1, what is the actual sequence in which this count equal to count plus 1 will be executed? So this simple statement of count equal to count plus 1 will be broken into a number of assembly level language, number of assembly instructions, because count equal to count plus 1 is a high level language. Okay. And count, what is count? Count is nothing but a memory location, some location in the memory which is assigned to variable count. Okay. So whatever is the content of that memory location, that is the value of count. So when this count is to be incremented, the number of assembly language instructions which will be executed to execute this statement will be something like this. Some register in the CPU, let us call it register R1, will be loaded with the value of count. That means the memory location which is assigned to variable count will be read, and the data will be placed into register R1. After that, register R1 will be incremented by 1, so R1 will become R1 plus 1. Okay. Following this operation, the value in R1, which is now incremented by 1, will be written back into the memory location assigned to variable count. So the last statement assembly statement which has to be executed is count is equal to R1. Okay. So this simple high level language statement of count equal to count plus 1 now is broken into these three assembly language statements, and when these three assembly language statements are executed in this sequence, then only I have incrementation of variable count by 1. Okay. Similarly, the decrement operation count equal to count minus 1, which is performed by the consumer process, will be similarly broken into a number of assembly language statements. Now let us assume that register R2 of the CPU will be executed for decrementation purpose. Now R2 and R1 may be same. Okay, they may be the same registers used by two different processes at two different instants of time. Okay, but there is no harm if I assume R2 to be different from R1. So the operations that will be performed is R2 equal to count, then R2 is decremented by 1, and finally this decremented value of R2 is written back into the memory location assigned to count. Okay, so these are the three assembly language statements which will be executed in sequence to give you decrementation of variable count by 1. Okay. Now let us assume that this is statement A, this is statement B, and this is statement C, this is statement D, this is E, and this is F. Okay. Now recall that when we have discussed about the CPU scheduling or process scheduling, what we have said is if I follow round robin scheduling or some preemptive scheduling, in that case it is possible that you forcibly terminate one process which is being executed by the CPU and allocate the CPU to some other process for execution. Okay. So this being a part of consumer producer process and this being a part of consumer process, it is quite possible that while the producer process is being executed, in between there is some scheduling which terminates the producer process and allocates the consumer process to the CPU for execution. Okay. So it is not ensured that when the producer process is being executed, all these three statements A, B, and C will be executed, then only for the consumer process D, E, and F will be executed. Neither it is sure that for the consumer process D, E, and F will be executed in this sequence, followed by A, B, and C statements of the producer process to be executed. So I can have an execution sequence like this. Firstly, statement A from the producer process is executed, then statement B also from the producer process is executed. After that, the statement which is executed is D from the consumer process, E from the consumer process, followed by C from the producer process, followed by F from the consumer process. This is a possible scheduling. The CPU scheduler or the process scheduler may schedule these tasks in this interleaved manner. Okay. So when the task is scheduled in this interleaved manner, let us see what problem we can face. The problem may be that at any time instant, let us assume that the value of count was any value, let us say 7. Okay. That means at this particular instant of time, there are 7 items present in the buffer. Okay. Now in this situation, let producer process produce one item, put into the buffer. Consumer process also consumes an item from the buffer. Okay. So the value of count after the producer process puts an element into the buffer and the consumer process consumes an element from the buffer will remain 7. Because producer process will increment to 8, consumer process will subsequently decrement to 7. Or maybe the consumer process first decrements to 6, then the producer process again will increase it to 5, increase it to 7. Okay, so the value of count after producer process and the consumer process does their job, the value of count should remain to 7. But in this sequence, let us see what happens. First, since the statement A is executed, so what we get is the value of register R1 will have a value 7 because count is not yet changed. So R1 gets the value of count and count is equal to 7, so R1 gets the value of 7. Right. After that, in statement B, R1 is incremented. So R1 becomes 7 plus 1, that is equal to 8. Sorry, 7 plus 1. So this becomes, R1 becomes 8. After that D is executed, now find that the value of count has not become 8. It is only the value in register R1 that has become 8. Count will become 8 only after this statement, that is count equal to R1, when value in R1 is written into location count. Okay. So at this point, we have a rescheduling when the producer process is terminated and the consumer process starts execution. So here, value of R2 will also be 7 because count is still 7. Then in E, R2 is decremented by 1, so R2 becomes 6. Following that, we have producer process which writes the value of R1 into location count and value of R1 is 8. Okay. So in statement C, 8 will be written into the location assigned to variable count. That means value of count becomes equal to 8. Okay, because it is R1 which is written to location count. And after that, in statement F, it is the value of R2 which is written back to location count. So count becomes 6. Okay. Obviously, that should not be the result. Our result should be after execution of both of them, count should remain 7. But I am getting a wrong result. Similarly, if these two are interchanged, F becomes first, say D, E, F are executed, then C is executed, then value of count will be 8. Both of them are wrong results. Okay. So this is a kind of problem that we will face if I don't take any extra precaution to protect the variable count. And of course, you can also guess this kind of discrepancy because we have said when we discussed about the condition of concurrency. See, producer process and consumer process, they are nothing but two concurrent processes. Both the processes modifies the value of count. That means variable count is in the right set of the producer process and also in the right set of consumer process. Okay. And we have said that if two modules or two statements are to be executed concurrently, in that case, their right set should not intersect. Okay. But the way we have written the producer process and the consumer process, that even if their right sets are intersecting, we have allowed to run them concurrently. Okay. So this gives you a situation that if the right sets intersect and we allow the processes to execute concurrently, then what kind of ambiguous result we can have. Okay. So just to highlight that the kind of ambiguity we can have, I have taken this example. Of course, this is just a special case of a class of problem which in operating system is normally called as a critical section problem. So this problem is known as critical section problem. Critical section problem or critical region problem. Okay. So the regions, wherever the value of a shared variable, because count is a shared variable which is shared by both the producer process and the consumer process. So the regions wherever a shared variable is to be modified, that has to be tackled in a special way, because this kind of problems are called critical section problems. Okay. So what is the possible way? Whenever one process executes in the critical section, and what is that critical section? It is a part of the code where a shared variable is going to be modified. Okay. So we must ensure that whenever one process executes in the critical section, no other process should be allowed to execute in the corresponding critical section. Okay. That means whenever the producer process is trying to modify the value of count, the consumer process should not be given access to the variable count, and vice versa. Whenever the consumer process is going to modify the value of count, the producer process should not be given access to the variable count. Okay. That means access to the critical section must be mutually exclusive. Only one process should be allowed to enter in the critical section at a time. Not more than one process should be allowed to execute the critical section simultaneously. Again, simultaneously means in time interleaved fashion. Okay. So coming back to this example, we must ensure that if the producer process has started executing this assembly statement A, the producer process should complete execution of A, B, C, all these three together. That means this statement of count equal to count plus 1 should be considered as an atomic statement. Okay. So only when all these three assembly statements are executed by the producer process, then only the producer process can be preempted, and access should go to the consumer process. And when the consumer process starts execution of this statement, all these three assembly statements D, E, and F must be completed before the consumer process is preempted. Okay. So when the producer process started execution of any of them, consumer process cannot be given access, cannot be allowed to execute these instructions. Okay. So that is what is meant by mutual exclusion. That is, to solve this critical section problem, we must ensure that the critical section is mutually exclusive. Okay. So the first requirement of a solution to the critical section problem is mutual exclusion. Okay. And we'll refer this as ME in future. Right? It is a part of the code, part of the program, where the process tries to modify some shared data. It's a part of the program, it is not an area in the system. Okay. The second requirement of the critical section problem is what is called progress. Okay. And the third requirement of any critical section problem is called bounded waiting. So mutual exclusion is clear that only one process should be given access to the critical section at a time. Okay. Of course, there can be more than one processes whose critical sections are not intersecting. There is no harm by interleaving such processes. But the processes which share the same critical region, they cannot be interleaved. Okay. Say for example, if we have some other process which instead of accessing this variable count, that tries to access some other shared variable. Okay. And that shared variable may be shared by some other processes, not by this producer process and this consumer process. Okay. So what this mutual exclusion says is the processes which share the same critical region, they cannot be interleaved. But the processes sharing different critical regions, a process accessing one critical region, another process accessing some other critical region, if they are interleaved, there is no problem. Okay. So when I say mutual exclusion, it is mutual exclusion of the same critical region, not different critical regions.
Is there any price we pay for doing this mutual exclusion? Like loss in speed or something?
Loss in field.
Loss in speed or execution or concurrency?
Yeah, concurrency is suffered because in these cases we cannot run them concurrently. If we run them concurrently, that leads to problem. So concurrency will suffer. In fact, these are the regions where the concurrency has to be stopped. So this mutual exclusion requirement is clear. Now let us see what is progress requirement. When I say that any solution to a mutual section problem, critical section problem or critical region problem must meet these three requirements. One of them is mutual exclusion, the second requirement is progress, and the third requirement is boundary weighting. Okay. So what is progress requirement? Progress requirement can be put something like this. Suppose we have a set of processes, n number of processes, say P1, P2, up to Pn, n number of processes which share the same critical region. So the same critical region is very important, not different critical regions. So P1, P2, Pn, these n processes, they share the same critical region. Okay. Now, if all of these processes tries to enter the critical section at a time, then we must ensure that only one of them will enter the critical section and others has to wait in some wait loop. So only when the first process, let us say process P2, if following some criteria, we have allowed process P2 to enter into the critical region, then all other process P1, P3 up to Pn, they must wait as long as P2 is executing in the critical region. So only when P2 comes out of the critical region, then only among the remaining processes P1, P3, Pn, again we have to select one process and that should be given access to the critical region. Okay. So that is what is mutual exclusion. It is also possible that all these n processes are not interested to enter the critical region at a time. Maybe a subset of that is willing to enter the critical region and others are not willing to enter the critical region at that instant. Okay. So the progress requirement says that the decision about which process should enter the critical region, that should be taken based on the processes who want to enter the critical region. The processes who does not want to enter the critical region, they should not take part in this decision making process. Okay. And this decision that who will enter the critical section must be taken in finite time. Okay. So that is the requirement of progress. That is, the decision about who enters the critical section must be taken by considering only those processes who want to enter the critical section, and this decision must be taken in finite time. Okay. Then the third requirement of a critical section problem solution, that is bounded weighting. Okay. So what is this bounded waiting? Whenever a process puts a request for entering the critical section, it is not guaranteed that the process will be able to enter the critical section immediately. It has to wait. It may have to wait because there may be another process executing the same critical section. Okay. So this bounded waiting says that when a process has put a request that it wants to enter the critical section, after that, the number of processes entering the critical section and coming out of the critical section before the request of this process is entertained must be finite, must be bounded. Okay. So if a process Pi has put a request to enter the critical section at time say t naught, right? So at time t naught, Pi has just put a request that it wants to enter the critical section. It may not be able to enter the critical section immediately because there may be another process executing in the critical section. Okay. So after the process which is executing in the critical section that comes out, then only Pi can be considered for possible entry into the critical section. But even then, I'm not sure whether Pi can enter or not, because there may be other processes waiting in the queue who also wants to enter the critical section. Okay. So again, the decision has to be made from among those processes who are willing to enter the critical section. Okay. So because we have to take a decision at that point, it may so happen that a process Pj, which was earlier executing in the critical section, has come out and has come out. Immediately after coming out, it can also put a request for entering the critical section. Okay. And it may so happen that now there is a competition between Pi and Pj. Pi has put a request to enter the critical section. It could not enter the critical section immediately because Pj was executing in the critical section. Pj has come out of the critical section, and immediately after coming out, it has again put a request for entering the critical section. Okay. So now I have a situation that Pi and Pj, both of them are in the same state because both of them want to enter the critical section. Now the scheduler has to decide that which one will enter the critical section, right? So it may so happen that instead of Pi, it is the process Pj which enters the critical section again. And this may go on indefinitely. That is, Pj comes out of the critical section, enters the critical section again, comes out of the critical section, enters the critical section again, and Pi is kept on waiting for entry into the critical section. Okay. So this bounded waiting says that when a process Pi puts a request for entering the critical section, number of other processes who can enter the critical section before Pi gets the entry into the critical section must be bounded. Okay. That is, a process should not wait indefinitely to get entry into the critical section. So these are the three requirements of any solution to a critical region problem. Okay. So accordingly, whenever we have a critical section in the code, the entire program can be broken into a number of sections. Obviously, I have a section called a critical section. Okay. So for any process, before the process enters into the critical section, there must be some additional job to see whether the process can enter into the critical section or not, or when the process can enter into the critical section. Okay. So that decision has to be taken by another part of the code, which is called an entry section of the critical region. So this is called entry section. So in the entry section, the process will put a request that it wants to enter the critical section. Then a part of the code will decide whether this process can enter the critical section or not, depending upon whether any other process is there in the critical section. Okay. Now, if the process is allowed to enter the critical section, then we must have some locking mechanism. That is, this critical section has to be locked, and which will be unlocked when the process comes out of the critical section. Okay. So a lock has to be set in the entry section when the process enters the critical section. And that lock has to be checked by all other processes to see whether the critical section is free or not. Okay. So all these operations are to be done in the entry section. Once the entry section is successful, then only the process, say Pi, can enter the critical section. So this is the situation of process Pi. When the process Pi comes out of the critical section, then whatever locking and other things that we have done, that must be unlocked. I am just using the locking term. Okay. So if there is any locking of the critical section that has been done in the entry section, then that must be undone so that other processes who wants to enter the same critical section can enter the critical section. Okay. So that is a part of the code which is called exit section. Okay. And the remaining part of the code is called a remainder section. Okay. So for any process who wants to enter the critical section or who has a critical section, it must have two other additional sections of the code. One section is the entry section and one is the exit section. In entry section, the decision has to be taken whether the process can enter the critical section, and also some locking mechanism has to be done if the process is given access to the critical section. Similarly, whatever locking you have done in the entry section, that must be done in the exit section, that must be undone in the exit section, so that other processes willing to enter the same critical section can get access to the critical section. Because if it is not undone, then no other process will be able to enter the critical section. Okay? And the part of the code which is neither part of critical section nor part of entry section, neither of exit section, that is called a remainder section. Okay. So this should be the usual structure of any program employing any critical section. Okay. Of course, it is not necessary that this remainder section has to be only on this side. I can have a part of the remainder section before this, part of remainder section after this. I mean, it is the part of the code not involving any critical section. That is what is called a remainder section. Okay. So now let us see that what kind of solutions we can have. Okay. I'll try with different attempts. Try to highlight what is the problem with the different attempts. Then finally come to a correct solution. Okay. So initially, let us assume that we have two processes, a process P1 and other one is process P2. A very simple natural solution that may come in mind is, because I have got two processes, let us have a shared variable which can assume either value 1 or value 2. Okay? So if the value of the shared variable is equal to 1, process P1 can enter the critical section. If the value of the shared variable is 2, process P2 can enter the critical section. Okay. So the situation will be something like this. In the entry section, I can check that, let us call that shared variable as turn, because it decides that whose turn it is to enter the critical section, and turn can assume a value of either 1 or 2. Right? Then for every process, the entry section can be written like this: while, let us assume that this is ith process. I may be 1 or I may be 2. So this is process 3i. So in the entry section, we can write that while turn is not equal to I, do So this is just a waiting loop. Okay. So when turn is equal to I, then only this ith process can enter the critical section. So following this, I can have the critical section. When the process comes out of the critical section, it sets the turn for the other process. Okay. So in the exit section, it will simply do the task of setting value of turn is equal to j. Okay. So if I is equal to 1, j will be equal to 2. If I equal to 2, j will be equal to 1. Okay. So this can be a simple natural solution that can come in mind. But is it a correct solution? So you find that process P1, if it finds that the value of turn equal to 1, it will simply enter the critical section. And in the exit section, it will set the value of turn to 2, so that next time process P2 can enter the critical section. Okay. So obviously, this satisfies one requirement of the critical section solution, that is mutual exclusion. Isn't it? Because this while loop guarantees that two processes will not enter the critical section simultaneously. Simply because though turn is a shared variable, but it's a single variable, and it can only assume one value at a time. Turn cannot assume more than one value at a time. So because turn will have only one value, either 1 or 2, so one of the processes, either process P1 or process P2 will enter the critical section. Two processes cannot enter the critical section simultaneously, right? While coming out in the exit section, the process which is coming out, that sets the turn for the other process. Okay. So if it is P1 which is coming out of the critical section, P1 will set turn equal to 2. So next time in this while loop, process P2 will find that turn equal to 2 and P2 will enter the critical section. But process P1 will find that turn equal to 2 because turn can assume only one value. Process P1 will also find value of turn equal to 2. So P1 will not enter the critical section. Right? So this ensures that mutual exclusion requirement is guaranteed. But what about others? So mutual exclusion is guaranteed. What about progress? In the progress requirement, we have said that from all the processes who share the same critical section, only a subset of that, if they want to enter the critical section, then the decision about who will enter the critical section, that should be taken only from the processes who want to enter the critical section. The processes who don't want to enter the critical section, they should not take part into this decision making process, and this decision must be taken finite time. Okay. Now let us take a hypothetical situation. That suppose initially value of turn was equal to 1. Process P1 wants to enter the critical section, so it has entered the critical section. Because turn is equal to 1, P1 can enter the critical section. Then process P1 comes out of the critical section. While coming out, in the exit section, process P1 has set the value of turn equal to 2. Okay. But it may so happen that process P2 does not want to enter the critical section at all. Right? But next time, process P1 wants to enter the critical section again. But P2 does not want to enter the critical section. So again, P1 will enter this entry section. In the entry section, it will find that turn is equal to 2. So P1 cannot enter the critical section. Okay. So indirectly, though process P2 does not want to enter the critical section, but because the value of turn was set to 2 by process P1 in the exit section, so indirectly process P2 is also taking part in making the decision of whether P1 can enter the critical section or not. Okay. Now when can turn be equal to 1? Turn can be equal to 1 in the exit section of process P2, because only in the exit section of process P2 will set the value of turn equal to 1. But because P2 does not want to enter the critical section, so obviously it will not enter the critical section, it will not enter the exit section, so value of turn will never be set to 1. And because value of turn will never be set to 1, process P2 will not be able to enter the critical section at all, though it wants to enter the critical section. So indirectly, the decision making process also depends upon process P2, who does not want to enter the critical section at all. Right? So this progress requirement is not guaranteed by this solution. Okay? So obviously, though it appears to be a very simple solution, it meets only one requirement, that is mutual exclusion. It does not meet the second requirement, which is progress. So it cannot be a desired solution for this critical region problem. Okay. Second approach can be that let us slightly complicate our control structure, our program structure. That instead of using only one variable turn, let us assume that we have an array. Let us assume that we have an array called flag, right, which is an array because we are considering only two processes. So let us have this flag as a two-element array of type Boolean. And it is also a shared array. And both the elements of this array are initialized to value false. Okay. Then, if a particular element of this flag is equal to true, that means that corresponding process is in the critical section. That is, if array 1, that is the first element of the array, is true, that means process P1 is in the critical section. If flag 2 or flag 1 is equal to 1, that means the flag 1 equal to true, that means the second process is in the critical section. Okay. So we can write the code like this for process Pi, where I can have a value of, in this case because it is 0 and 1, the indices are 0 and 1, let us assume that I can have a value of 0 or 1. So I can have process P0 and I can have process P1. Okay. The entry section can be written something like this, while flag j, that means flag j is true, do skip. Okay. So if process P1 finds that flag 2 is equal to true, that means process P2 is in the critical section. So P1 has to wait in this while loop. If flag 2 is equal to false, that means process P2 is not there in the critical section, so P1 can enter the critical section. Before entering the critical section, it should indicate that P1 is in the critical section, right? So for that, what it has to do is, it has to set its own flag, flag I is equal to true. Okay. Then process Pi can enter the critical section. So this becomes our entry section, and this is the critical section. Similarly, in the exit section, what it has to do, process Pi has set flag I equal to true, indicating that process Pi is now executing in the critical section. While coming out, it should set flag I equal to false. So in the exit section, we have to have flag I equal to false. Okay. So this is the second simple solution that can come into mind, right? Now, if you want to analyze this, you find that initially both the elements of this array flag are false, right? So if at any point of time there is no process executing in the critical section, both the elements of flag will be equal to false. Okay, that is also ensured in this exit section. Now we can have a situation like this, that both the processes P1 and P2, they want to enter the critical section. So P1 will execute this while flag J do skip. It finds that flag J is equal to false, assuming that process P2 has not executed this statement yet. Okay, so it will find that flag J equal to false, so it will set flag I to true, enter the critical section. Right? Now, if the situation is something like this, that process Pi has executed this while statement, it finds flag J is equal to false. So because flag J is equal to false, so while loop will be broken. But ith process has not started execution of flag I equal to true. In between, I have the preemption of process Pi. And process Pj executes the corresponding while statement. So when process Pj executes the corresponding while statement, because flag I has not been set true by the ith process, so jth process will also find flag I equal to false. So while loop of the jth process will also be broken. So subsequently, process Pi will set flag I equal to true and enter the critical section. Process Pj also will set flag J equal to true and will enter the critical section. So we find that if I have this simple mechanism, then also both the processes can enter the critical section. Right? So that means the first requirement of this critical section solution, that is mutual exclusion, that itself is not guaranteed by this. So even this cannot be a desired solution. Right? The other option can be that let us interchange these two. So right now, flag I equal to true indicates that process Pi is executing in the critical section. If I interchange these two, that will indicate that if flag I equal to true, that means process Pi wants to enter the critical section. Pi has not entered the critical section yet. And then you bring this while loop. Okay? After that, you have the critical section. You try this option and see whether you can face any problem or not, or that gives you the correct solution. Okay. So with this, we stop here today. We'll continue in the next class.